welcome to Beyond the Qubit. I'm your host, Frank Dekker. The guest of today is Thomas Ohki. Thomas is the CTO of Emergence Quantum. And I really look forward to interview Thomas because Emergence Quantum is a special company. At the moment, they're not yet relying on external financing. They're funded on customer and partnerships. And Thomas has a lot of experience. He has a long tenure in the quantum industry and he tries to optimize for the long term. And he tries to solve bottlenecks in the quantum value chain. And the specific focus of Emergent Quantum is cryo-CMOS, but they have multiple, they research multiple problems across the value chain. Before we start the podcast, I have an important disclaimer. The podcast is under personal title and I do not represent any company out there. With that, let's get started. One of the areas Emergent Quantum focus on is cryogenic control electronics and integrated cryo-CMOS. Can you explain in simple terms what cryo-CMOS is and what solutions does it bring?
Right. So personally, I have worked on cryogenic electronics that span semiconductor technology, CMOS or superconductors. The goal is this. We'll get to the goal first. You want to create some electronics that are able to control quantum systems and not decohere those systems, which means don't spoil the quantum system. Like you have to maintain its quantumness in order for the devices to work, whether it's a computing system or a sensor. So that means you have to design circuits that are low power enough, don't produce noise, don't have any other deleterious effects that would impact your ultimate performance. So that's what
Thomas, if you say low power enough, can you compare for the listeners? How does the energy budget compare to a normal AI GPU? So what is the power limit that you have to work with low enough power versus the normal power today, just to give a perspective?
Yeah, I mean, I think the power density we're talking about is orders of magnitude different. So thousands, hundreds, even hundreds of thousands of different, right? Like, so you're operating at temperatures that could be, like you said, very deep cryogenic. So millikelvin temperature, 1 Kelvin, like below liquid helium temperature. So those types of circuits, many circuits require microwatt, 10 to the minus 6, so a millionth of a watt per qubit or so, right? Where modern processors, GPUs, you're expending so much energy that your devices are heating up well above room temperature, right? And so the disparity in power density it's not even really comparable. It's not the same technologies. If you think about it, the design principles of circuits that operate cryogenically, you're minimizing it completely. Only bare functionality. Like, so whatever you need at the very, the simplest instructions you have to put down. The least amount of flexibility in some sense is what you're engineering around there. So it's challenging from that regard. You don't have a lot of freedom to do things because of that constraint. But it does enable you, to your point or question, it enables you to think about not only measuring a few qubits or quantum devices, sensors, really one of the only ways to get to the millions of devices that many people are envisioning for large computing platforms. And so that is what it enables. It allows you to think of new structures, architectures for designing a system so that you're getting around some of these bottlenecks that I mentioned, like the I/O bottlenecks and things like that. So it enables flexibility in architecture, the ability to do things you could not before. And that's true for not only cryo-CMOS, but other technologies that fall into that category, things that could be interfaced
Thomas,
with qubits.
Can you explain the audience why that is the case?
Sorry, why that...
You said it provides
clarify?
Flexibility and it enables also scaling up to 1 million. Why does this solve the bottleneck?
Yeah. Well, for instance, you can't just use CPU or GPU from your normal computing system and place it at any lower temperature.
I'm with you. That's clear.
Yeah. So if you're already sort of, if you already basically agree with the premise that there is an I/O bottleneck to processors, and there was a requirement to do more direct engineering through down to the quantum processing unit for many of the systems.
Sorry, let's take one pause. So for me and for the listeners, so at the moment, if you scale the amount of qubits, the amount of I/O increases as well.
Right.
So maybe from 1 qubit, you have maybe 3 control lines.
Right.
So if you go from 1 qubit to 1 million qubit, that would mean you have 3 million control lines. And that is the I/O bottleneck that you described. Is that correct?
Yep.
And to your point, how can you solve the I/O lines going from the input-output lines going from 3 up to 3 million? So what solution do you have to make that easier and to solve that?
Right. So the solutions are, the reason why the line scale, as you mentioned, is that in order to operate the computing system, you need control, typically individual control of each qubit. So that's why it scales to so many I/O lines. The technology that we create...
Thomas, for the listeners, you need the individual control of the qubit lines because it's in-memory compute. Is that correct?
Well, it's...
Or are there also other reasons?
Well, it's not necessarily, I would say, in memory, but at this point in time, the ability to recycle signals to multiple qubits, meaning reduce the number of lines because every qubit would require identical signals, that's actually still not possible. And it's going to be hard to imagine that will be the case necessarily moving forward, especially for platforms that are nano or microfabricated devices. So that being said, there are a lot of ways to reduce the number of input lines that come from a larger control system that send lower frequency, slower data that tell you what needs to be sent to your quantum layer. So what you're taking are instructions, more so of what to then translate down to the quantum plane. And in that case, what you can do then is remove the high bandwidth, large number of interconnects that you have from a specific portion of your control architecture throughout, say, like a cryogenic environment. One of the biggest challenges actually is just even the number of lines you would need from, say, even a 4 Kelvin environment up to room temperature. The amount of signaling that you would need for many of these systems would render a lot of the fridges useless in most cases. You wouldn't be able to cool. There's not enough cooling power. So those are some of the practical constraints as far as the cooling power that's enabled by the fridges to allow you to scale those lines as well.
And that are the problems where Emergence Quantum is working on.
Those are definitely the problems that Emergence Quantum are working on. So we are looking at conventional systems. I think that are really cool
problems to work on, Thomas.
Yeah, they're not easy ones either. I think it's one where it will transform how these systems look and how you can conceive of what a quantum computing system will end up looking like in the next 5 to 10 years. So those are challenges that we're excited about, and we're developing, like I said, some hardware solutions to attack those problems.
And Thomas, what are the main obstacles, engineering obstacles, when integrating classical control electronics closer to the qubits, like thermal load, noise, interference, or wiring density?
Those are, you named a lot of them already. So each application, each quantum technology that you integrate with has its own sensitivities to thermal noise. So specifically engineering noise to match with the constraints and specifications for the target systems has to be done. Thermal effects just from heating. You have to understand how packaging is developed and how it behaves as far as materials, interfaces. Thermal transport at low temperatures typically is a pretty underexplored area and will be a huge area of engineering in this field matures as advanced packaging becomes more commonplace too, like things like 3D heterogeneous integration starts to become more commonplace. The other aspects are just basic design of circuitry that functions at low temperature with good yield. You can make experimental demos of things, but if you're talking about building something that could function with a high level of reliability with thousands of devices on it, now you start to talk about even not only there's challenges on the qubit side, but you have to build a circuit that is optimized there and will function and have a high amount of reliability, right? And so that means there's a whole area of development of custom low temperature design kits and things like that for CMOS technology or other superconducting technology. So things that would be there to enable reliable and robust design of the more complex, say, digital or analog blocks as well. So that's another challenge. So you're just scratching the surface of the really of the challenges that would be required in this area. So, but those are some of the biggest, I think. So.
Okay. And on your technology roadmap, what problems are you trying to solve the coming 3 or 5 years?
So the next, in the area of quantum computing, the next 3 to 5 years, what we want to provide is an ability for quantum computing platforms across a lot of different technologies. And so we're aiming to address challenges in ions, semiconductor qubits, superconducting, photonics, build enabling technology to get to the next scale in computing complexity for those quantum systems. So technology that would allow for scaling to tens of thousands, hundreds of thousands of qubits. And that's where most people's roadmaps are going in the next 3 to 5 years. And so we want to work with companies and co-develop those technologies with them. And the company's aim is to not only be involved in research with clients and customers like that, but to be able to provide technology that could be productized out of that as well, to feed into the supply chain, which will be part of what these computing companies will need in the future. So that's the goal in the next 3 to 5 years is to be able to fulfill that particular area of growth for those companies and enable that, but also provide a solution to some potentially challenging supply chain aspects.
And Thomas, what solution gets you most excited at the moment that you say, well, this really drives my energy and I think that can really solve a bottleneck in scaling up the amount of qubits?
Right. So there are so many challenges at the qubit level, and I think you'd be remiss without saying there's been an amazing amount of work that's gone into that level. But I do feel like the next frontier of scaling will be to see for many of the systems that could scale quickly, meaning there's a few platforms like semiconductors could scale quickly where those also require very close proximal circuits for control and readout. I'm kind of extremely excited, but at the same time, that is one area you can't be excited without there being some sort of risk involved. But that one seems like some of the most interesting. There's other platforms that are requiring a significant amount of co-integration and co-location. How that performs in the next 3 to 5 years at some level of scale, and if you can retain performance of those systems, that has me very excited because that means you can unlock a lot with that approach. If we find there's a fairly positive response, these systems are robust against the things that we think about, and you can actually get to a level of some co-integration that allows you control circuits or readout circuits nearby, that will be a big shift in where the field is today. I can't pin down exactly the technology that specifically makes me excited for that, but that is I would say a technology leap, which I'm excited for. There could be a very diverse set of hybridized technologies within that, and it relies on so many things that we just mentioned, right? From advanced
Thomas,
packaging and onwards.
The way I think about it is roughly with 2000 logical qubits, the first applications are possible. And then at the moment, superconducting says, okay, at the moment the error correction ratio is improving from 1000 to 700. But when I speak to IQM or other platforms, they say we can go as low as 2030. If we assume a little bit more conservative, if we assume error correction ratio of 50 for superconducting, then if you have 2000 times 20, you need 100,000 physical qubits.
Right.
And of course, ion trapped with Quantinuum has much better error correction ratios. But each technology has, I'm comparing it on 3 things. The scale up, so how many qubits can you have per chip?
Right.
How many qubit chips can you have in a cluster? And what are the improvements on the error correction ratio?
Yeah.
Do you mentioned, okay, I see important breakthroughs. Where do those breakthroughs fit? Is it on the scale up? Is it on the scale out forming clusters? Or is it on the error correction ratio? Or all of them?
Well, it's almost all of them in some sense. So it's kind of the one interesting part of being able to build a lot of control systems which would solve your I/O challenges, meaning be able to scale up in that sense quicker, means that you're potentially getting up the ladder on this error correction complexity side sooner. And what I mean by that is this, that error rates are inevitably going to improve in physical qubit systems. Each one's going to improve at some different rate. But the one thing you can throw at it is if you're okay with the increase in complexity, what's called sort of like, in some cases, code distance, like how big your circuit is, like how many physical qubits have, you can use more physical qubits if you're all right with the overhead that presents itself. And so there's, in some cases, yes, it's great to use qubits that have wonderfully low error rates. That means your error correction ratio is going to be better, or at least the distance of your codes will be smaller. But, that there is an area or a knob to turn where it says, okay, well, if I make one thing a bit simpler, maybe make larger systems that potentially have larger error rates, but I can tolerate that, then that opens up a bit of a space to start accelerating more, right? Rather than waiting for physical error rates to improve or individual qubit error rates. The other aspect is this. It's like there are other systems which are really pristine platforms, individual error rates. Like you mentioned ion traps, like Quantinium is a good example. Those are excellent individual qubit systems. It's just the scale up requires some of this engineering that we're talking about, where it's co-located hardware that enables you to really solve some of the I/O challenges there, really think about how you'd build a much larger system and things like that. So that also is another, knob to turn. So I think it impacts a lot of different aspects. Like you can solve the challenge of like, oh, well, the total footprint of single qubits is larger for this platform, but it might be actually an easier challenge to solve to grow. There's another platform where the error rate might be not as good, but it could operate with, maybe it's more robust to CMOS integration or whatever technology. And you could scale the error correction circuitry much larger for that because you're afforded that. So there's these directions you can go in, which it just makes the field extremely interesting at this point. That's actually one of the main reasons why our company is not going to necessarily just choose a single technology and design everything around that at this point, because we don't necessarily see a clear winning technology yet, but they all have some common threads to work on that we are definitely poised to really focus on as a company, as a solution provider that can answer these questions, can help to start answer these questions more. So that is a driving force in the company's philosophy as well. I think you're kind of pointing that out indirectly here.
Okay. Can we talk a little bit about your recent partnership with IQN to develop electronics and materials for ion trap systems? What is the scope and timeline here?
So with IonQ, you mean, right?
Yes.
Yeah, okay. So IonQ's, we have a partnership with them that we are really looking at developing hardware that would, like I mentioned before, some of the technology for shuttling ions around requires electronics to drive electrodes and do that in an efficient manner. Obviously, things related to shuttling photons around that interconnect traps as well. But those types of technologies we're in the process of setting up projects with IonQ to explore development. They have a roadmap of their own, which I'm not going to talk about. They're likely going to publish things on their own to discuss that.
I don't want any non-public information.
Yeah. So they in that sense, what we're doing is helping them to develop the core technology towards that roadmap, right? And, it's no surprise they've recently begun, or at least acquired Oxford Ionics, which is also working on trap technologies and other types of integrated electronics. So there's a clear direction that company is going in, and we hope to be part of their long-term team that's helping advance that. And so our expertise, what we've discussed already, is looking at how to solve some of those challenges where there's integrated trap electronics, integrated control systems that help interconnect traps and things like that. And so it's all super exciting because it's getting to the next step is a huge challenge with those platforms. And like I mentioned, it unlocks a whole host of new opportunity if that's successful. So we are starting on that journey with them. Really, it's just something that's kicked off. So I can't really say too much more about it at this point.
Who do you see as Emergence Quantum closest competitors or peers, and what differentiates you?
Yeah, so you mentioned a couple of companies that develop control electronics. We don't think those are competitors. In fact, we think they're collaborators. The amount of people in the space that we are sitting in right now, there's not that many that are in that area. I think largely there's companies that have divisions, depending on how big they are, that have been working on scaling solutions. Whether you're IBM or you're Google or your other spin companies, there's Quantum Motion, there's other places like Dirac. Dirac is a company that we do work with. They all have people that are working in this area. So I think it's more that there's folks that have been in this arena from the company side, but they aren't their own company entity working in that area. So I wouldn't say there's a direct competitor, but there's people that now we're considering, as we work with companies, we'll start working with some of those internal teams, whomever they are. And that's more of the connection we have in the community than anything else. So there's probably a handful of companies, maybe I would say there's a company, Seek, that's working on superconducting solutions. I know that company very well. I've worked with them in the past. And our approach is a bit different than what they're doing and has a different application space. I think in general, we incorporate a lot of different technology. I think the differences to a company like Seek is that we're not really necessarily confined to particular technology bases. Like I think we're agnostic of the hardware that we're providing for the solution too. So cryo-CMOS might be something that the group has an expertise in, but it's not the only solution we bring to the table. So whatever gets the job done is what we'll focus on. And I think we have a diversity in the team to be able to accomplish that goal. And so that's what I would say would be the differentiators between anybody else that would be kind of close in the space.
How do you envision your relationship with quantum hardware providers, enablers, collaborators, or even potential acquirers?
A relationship. So we want to be really a trusted source or collaborator with as many quantum companies as we can. There's obviously scenarios where just based on interactions, we'd limit that because there's companies we want to work with that might have sensitivities of competitors, etc. So there's an aspect of working in the community which we are sensitive to and have a working relationship that we want to establish that makes that possible, so that there's no issues with that. But that being said, at this point, what we're doing is establishing the company and finding partnerships that make sense for us. And there's a few boxes that get ticked there: the quality of the approach, the people that are behind it too, and the longevity of that organization and where it could go. So we're looking for the right customers to work with. That's one stance as far as the rest of the community. So yeah, I would say that the acquisition question, that's another one. I think it's not obviously unheard of that companies are starting to acquire parts that make sense in their longer term roadmap. There's definitely some that are doing that fairly aggressively. I think what I had stated earlier was One of the major goals we have is to really set up an R&D entity as part of the main company. When we find that there's a customer in particular or a company which really moves in that direction, where they're like, there's something that we definitely want to tie much more closely to that company. I think we're structured or trying to structure ourselves in a way where, like I said, the main research company has the ability to spin out activity in different directions as we grow. So the strategy at this point is we will work with companies to grow, and once we see that there's a really good match, then I think there's opportunities to accelerate and tighten those relationships. But I think both David and I want to have a long-term entity that keeps progressing in this area, not just with that goal in mind, right? That's not really the goal of ours. So
let me try to summarize. I think what is important for you in partnership is that earlier in the interview you mentioned you need to set your own research agenda,
right?
Or have the flexibility to do that. You want to have to work with knowledgeable people, but from your very early days of the industry, you were already in this field, so you know and you have a lot of relationships, and you want to optimize for the longer term. And the goal is really to be a research company. And one of the benefits that all this brings is that you can be independent. So others might compete, whereas you can see as an independent collaborator.
Yep.
And maybe one of the biggest bottlenecks in the industry is talents. And you will be a very big source of talents. And is that, but then what is the business model? Do you charge by hour? Or do you also try to get IP if something? So imagine you have a massive breakthrough. If you have a product, for example, like Qubit or Delft Circuit, they productize the R&D and they sell products.
Yep.
But where you differ is you deliver the R&D. So can you help me understand as an investor, how does that business model work? How do you charge, or how do you make sure that you have decent margins?
Well, so there's, first of all, the engagement with customers. We're providing solutions. There's also lots of models for that, right? It can be very transactional, where the customer might just want something made. We can own all the IP and they get a part of their supply chain. To the extreme, where we work very closely with a customer, all the IP sits with them, and that will likely come at a premium with the work that's done, right? There's going to be rates that you charge. It's not necessarily hourly, but in the contract world, you judge it based on a few different ways. Like you can create something that's trying to hit an end goal, a deliverable. It could be a prototype. It could be something much more mature than that. So varying degrees of that. And in between, there's engagement models that can be a split of IP cores or IP blocks that we say that we're bringing to the table and we'll develop, that may only need to be licensed, or there's other arrangements, right? So there's a variety of ways that can happen, which makes both sides happy. As far as, that's one part of actually sort of the research engagement contract part. As a company, we'll be bringing in contracts that have, fees on them based on the engagement model. The idea is to use a lot of those profits from contracts and feed it back into R&D that's helping boost up, not only our own portfolio of ideas, that's some of it's just know-how, but turning that into IP that's internal to the company and having that be something where we can continue to bring new IP to the table, whether it's background IP, or at some point when we see that the market dictates that this is either for a single client, they're scaling so big that they just need something in their supply chain, and we can provide that. We just push that manufacturing out to a product. That's a possibility. It could be components out to big parts of the system. And that entity can move in a different direction from the main R&D sector. So there's lots of company structures that can enable this, right? And so that's some of the basic model of how we go about business for, say, the quantum computing space. So it does require a few different models. There's an interaction with customers, a kind of clear understanding of the IP arrangement, the ability to continue R&D internally, to develop our portfolio, and then the ability to also launch product efficiently when we find a window that we can do so. And there's either single customer or enough of an addressable market that we think it's the right time. So that's in particular for the quantum space, that's how we're approaching it. The other business lines have slightly different customer types and timelines, like energy efficient compute systems might be a very different model than that. But consider this as studio beyond the qubit, I think, giving you the idea of the qubit side of things.
Now, I'm also interested in sensing and also high performance compute. I think everything is very closely related.
Yeah,
and so I would love to hear.
We do too. Yeah.
I would love to hear your view on that, or maybe on the mix split. What percentage is quantum? What percentage is roughly sensing, and what percentage is alternative high performance compute?
Yeah, so there's no fixed ratio. It's going to be right now customer driven. Early on in the company's launching, we're very quantum focused, but I would say the second largest percentage now is the energy efficient compute side. And the reason is that we see an opportunity there. We strongly believe that there's a next generation tectonic shift, if you were to say, in compute technology that actually starts to go more cryo. We're pretty bullish about that. So I think there's
Thomas, why is that? Why do you think that the next tectonic shift in compute involves cryo? Because now you got me. You have my full attention.
Right. So we do think that there's only a few knobs that you can turn to improve compute systems, conventional ones, and one of the last remaining ones that we know, it's been shown that performance can be improved as far as performance per watt, efficiency, increased clock rates, can be by adjusting temperature. And that's even with conventional CMOS. Not to mention other alternative technologies that might be a little bit down the road, but in that path, like superconducting things as well. But I'm even talking about just conventional CMOS. And so we do think that there's a path forward there where that's a very intriguing direction. And the world has changed in the last 5 years. I used to sit in meetings and I was working in energy efficient compute in parallel to quantum for a long time. And the size of data centers, the energy cost of data centers, people were saying, 50, 100 megawatt data centers, you're not going to get much bigger than that because you need nuclear power plants to run them. And it's like, no one's going to do that, right? So things have changed a little bit, right? And so that, in addition to how people are cooling devices now, like liquid to chip and other things where the infrastructure, the energy expenditure, things that were unfavorable to alternative compute platforms are that story is changing a little bit. And so we think that there's a direction where not only, in quantum computing and quantum systems, cryogenics is almost a necessity now. There's a world where cryo starts to permeate the compute platforms that you see today and start to merge with quantum systems, edge technologies that are sensors as well. So the convergence of technologies, I think, towards the direction where you're going to be able to take advantage of improved performance by cooling even further than obviously things are done today in conventional data centers is an exciting one for us. So that's a space to keep an eye on. I think like I mentioned, we're working in that sector
Thomas,
as well.
You mentioned that there's only so many knobs to turn on, and you say, okay, if you move to lower energy in CMOS, that has benefits. But what benefits does it bring if you move to lower temperatures? Do you mean lower energy consumption, or less heating issues? I really want to understand what is the benefit if you move to lower temperatures in CMOS?
Yeah, so there's some studies over the last few decades that have looked at what happens as you cool that technology. I mean, there's some things that change immediately, like leakage effects. So you're already decreasing static power consumption of certain things. You can also lower certain threshold voltages, increase clocking rates and things like that without paying a penalty. So you're able to get more performance from just those aspects. And
why is that so? If you reduce so you said, okay, if you cool things down, then you have lower leakages or lower heat dissipation. Last week I was or 2 weeks ago, I was at the ASMI Investor Day, and they talked about the roadmap of ALD, atomic layer depositioning.
Right.
So I'm a little bit familiar, not as knowledgeable as you, but I'm fascinated by those kind of technologies where the impact is. Did you say it enables, if you cool it down, then it enables you to turn up the clock speed?
You can start to overclock circuits. You also have, the leakage effects are one thing, but you can also potentially, thermally broaden threshold voltages require you to have sort of also bigger swings and voltage across devices. So you can actually tune and change the threshold voltages. So people have been looking at low threshold devices in combination with dynamic savings in energy, because it's just your CV squared. You also have this leakage effect. So those things combined with some other aspects, optimal kind of design of circuits as well, you'll see these improvements. And it's not a matter of sort of theoretically whether that's the case. It's more implementing and making sure it's a commercially viable solution. It sort of wasn't ever, because the thought of cooling down anything beyond just with water cooling, it was basically a no-go. But so 20, 30 years people have been already doing this. In some applications, people have just absorbed the effect of doing that because they needed cryogenic implementation. Like, for instance, I was in the defense community for a long time. People built sensor technology that had to operate cold. Building readout and integrated circuits needed to happen locally. It needed to have some density. So people were forced to optimize devices for that temperature, But so there was a lot of learning already happening for the last 30 years in this community. But from the compute standpoint, there really hasn't been a lot of progress. But the analysis side, I think people have really looked into it. There just hasn't been a financial motivation to do so. But the changing landscape of compute now, and the whole evolution around what does energy consumption mean in these systems, and that's evolving everybody's thinking on the topic in general. So that's another exciting space to be. But like I said, there's these horizontals across computing, quantum computing technology that apply, like some of the tech development, like you're trying to optimize energy of the compute systems that you're building for the other platform. A lot of the challenges become kind of similar. Analyzing thermal properties of circuits operating at temperatures like that, not only just how an individual device functions, but how you design a system around that and how to remove heat and things like that. So those are all sort of relevant challenges that fit across all these platforms. And we didn't even talk about sensing, but sensing is another frontier there. I would say that...
Now, let's go into it. What are the main highlights of Emergence Quantum on sensing?
Right, so...
And Thomas, I have a lot of sympathy and for your thoughts that cooling principles should be applied to AI as well. And maybe that might be a bridge in high performance, the next tectonic shift. The problem
Possibly.
is that as an investor, with my limited understanding of physics and quantum technology, I find it, so my feeling says, yes, that's very logical, and I would love to, that thought came across me a few times, but I don't know how to research it or how to explore it further.
Right.
Yeah.
Well,
what would be your suggestions to me? What would you research if I want to explore this further? What are the best sources, or what should I read, or what are the things that you say, Frank, that are interesting things to pay attention to?
Honestly, this is a very hard question to answer, because like I said, there's been studies, like DARPA has done some studies in this, for instance, defense in the US. Cryocomputing has long been known as a viable aspect for CMOS. Again, that's like the cost of doing so versus the cooling requirements, etc. That's always been a challenge. There's not a lot that's in that domain that's just published and information. A lot of the development that I've seen, like I mentioned, is there's people who have done that on the defense side because they've needed to. So there's not a lot of really kind of open literature and sort of a lot of experiments in that area or people doing it. So it's somewhat a new nascent area in that regard. You will find a number of groups trying to build cryogenic electronics for quantum control and other things that are cryogenic, like mostly for other things, right? But not necessarily in its own right, as a computational, shift or paradigm, right? So what I will say is you should just watch the space that we're creating. And that might be the best advice I can give you at this point. So,
okay, so watch the cryogenic compute space. Is it correct?
Yeah, watch that space, and I think you'll start to hear more and more about that, and hopefully a lot from us.
Okay. Maybe what's the ambition level with sensing for Emergent Quantum?
Right.
And what do you try to achieve there?
Yeah. So the main ambition is that in my years at Raytheon, we had a quantum division that was looking at computing applications and scaling technology for that. Very similar to what our ambitions are at Emergence. There was always a dual use, and that always ended up being on the sensor side. And there was many aspects which interacted with other groups within the company. Like I said, there's a history in that for different either focal plane technology development or other types of ROIC, or readout and integrated circuit controls for imagers. A lot of that was developed for low temperature. They always had these interesting data bandwidth issues to higher temperature. So some of the things that we're talking about here, this I/O challenge, the local control, there's so many parallels in the sensing community, and that applies to not just what you can call quantum sensors. So there's quantum sensors that are like NV diamonds for magnetometers, other sort of atomic systems, even sort of non-quantum quantum application sensors like single photon detectors made of superconductors. So
we also had single quantum on the podcast.
Yep, that's right. So the those single photon detectors, or more quantum detectors, they require, like I mentioned, the same type of philosophy of integration, particularly when a sensor is more related to retaining quantum coherence. You have to be very careful about how you engineer that. So if you're already doing that with quantum computers, then it's almost a direct parallel to what you could do with other quantum-based sensors. The other aspect is, for instance, like single photon detecting technology. There's also an application in quantum computing where we're looking at working with photonics companies where that's a core part of their architecture and also requires some level of integration with those devices to enable scale up. Let's not even think about scale out, but scale up. Same can be said for other applications for single photon detection systems in arrays, integrating with photonic integrated circuits, control circuits that are now tightly integrated with those systems. The application areas for those are growing beyond their scientific applications. So the space for devices like that, we want to make sure our technology maps onto that space as well. Say a financial benefit for the company that we're diversified in these areas. It's a bit of a risk mitigation, because I always felt that in our previous group at BBN, we needed to have more conventional applications be addressed by what we're working on. There's ebbs and flows in every customer base. And so from a company perspective, this is just part of our diversification model. This happens to be a really great fit for a lot of the technology we're working on. So that is part of the ambition, but it's to enable amazing development on the sensor side. People are working on incredible new sensing technology. Oftentimes there's a gap between those innovators, whether they're even at the academic level or early startup company, then bringing it to a system or fieldable device that they could use. And so that's an area which I think we can help with our experience in system design and engineering, and then just at least the actual hardware development of those platforms with collaboration with those entities as well. So that's our main goal. It's very complementary to the rest of our work, but it's definitely not to be undersold, because particularly in Australia, it's a very big community. They're very focused on quantum sensing technology, new sensing technology and modalities. And so I think that's something we want to help support.
Okay, interesting. Can we talk a little bit maybe about, you just started the company for how many years?
Right.
1, 2 years, or how recent is it?
Not even. Like really, we started within the last, I would say, 6 to 8 months. Really is when we've been launching the company. So it's very new. But as I mentioned, it's not the typical startup where it's one or two founders coming out. And that's it.
Yeah.
We started the company with already 20 people in it, and a team that's worked together for 7 to 10 years.
Yeah, that's really powerful. I was wanting to ask how much IP do you have, but given the fact that you just started up, I think the amount currently is limited.
Yep.
What are the plans of building the IP going forward?
Yeah, so I think that is something exactly that we're doing now. As we're launching the company, we're putting our effort into understanding what our IP strategy is internally with internal projects that we want to get started right now. So that's building. Like I mentioned, part of our revenue model where we're bringing in contract profit will feed back into IR&D. We have to be very selective of what we are going to choose to patent. Right now, I think we're of the impression that a lot of this is going to be know-how, and we want to be able to have know-how that's in some sense applicable and transferable to a bunch of different clients. We do want to be specific about the background IP that we want to very much protect, but we are early days. At this point, one of the big things is just being flexible with people and customers. And so I think our focus is just really establishing those relationships at this point. And so I think we're pretty flexible about how the terms are during our interaction, or how they're determined.
Thomas, can you walk us through the customer momentum? And do you have concrete data points of proof that there's demand for the solutions?
So customer, I missed the first part of what you said. Customer.
So what is the customer momentum? So you're a research group, but what are the concrete data points that people want to work with Emergence Quantum? Because you're an R&D house. So what contracts have you signed so far? How many customers do you have? And also the volume of the contracts. How is it ramping? Or what is the momentum? Or what?
Yep.
What data points can you share?
Well, so what I can share is that, we have some published engagements right now with Dirac, who's a spin semiconductor company making CMOS qubits, essentially. The other one is IonQ, which we're working with. We're currently, there's quite a few more engagements that I can't mention right now, but those are in queue, and they're I would say the momentum is, we've got a lot of momentum at this point, and so...
Yeah.
The hope is, maybe I can put it this way, is that we want to be, as a company, we want to have our revenue targets met to, have the whole company employed under revenue from the business that we have within the next year, 6 months to a year. And so that's the scale at which we're targeting. That seems to be an achievable goal. And so from our perspective, we want to keep that momentum and actually just accelerate it. That's a pretty conservative estimate. And so the data points, what I can say is this: we're hitting the market at a very good time for engagements like this, meaning companies, particularly in the quantum space, they're mature enough at this point that they are looking for help to grow and keep up with their technical roadmap. It's very hard for many companies to bring in a team of domain experts that's worked together, kind of coherent understanding of what the problem is and can solve it in one go, right? Yeah, you can acquire a team, but having somebody work on a particular aspect of what you're doing that you think is kind of high risk or needs to be de-risked, or you just don't have the team, they're more willing these days to have that discussion because they're more mature companies. They have a understanding that they likely won't be able to tackle all the problems themselves. And so understanding how they fit within the ecosystem of other companies attacking the problem this is more commonplace than it was 10 years ago. 10 years ago, there was a lot of it wasn't invented here syndrome. That's not the case anymore. The data points I will say is that just the amount of conversations that we've had with people and where they are in terms of their technical roadmap, that gives us confidence in the direction where we're going, and gives us confidence that momentum will still persist and be there. So On the other sectors, I think, on the energy efficient compute side, it's hard to beat the momentum of anything that could provide a solution beyond where things are today. Because in general, the community is like wondering what's happening next. You can't keep scaling to the point where, either the capital costs of hardware or the energy costs, something in the end of the day is going to, start to become big enough that people need to implement alternatives. And that point is likely coming sooner rather than later. And so the momentum on that side is palatable. So the areas that we're involved in are moving at different paces and at different scale, but I think we're always feeling a really positive momentum of both. And so that's what I can say as a response.
Okay, thank you. Maybe one final question. Can you wrap it up maybe in 1 or 2 minutes and give a summary about Emergent Quantum and why investors and people who are excited about quantum technology, why they should pay attention to Emergent Quantum?
Right. So Emergence is not just another quantum computing company. It's a company that's going to solve problems on the next generation computing platforms that span quantum systems and also what's happening in the next generation of computing platforms for AI and data centers. The reason that people should keep an eye on Emergence Quantum is because the core technology that we're working on is what is going to be the key to unlock the future for what we feel is next for quantum computing systems. And the next 3 to 5 years is where you'll start to see the impact of the technology we develop make an impact on how those systems grow. So our involvement not only in quantum sectors, but the technology we build for data centers, we're hoping that becomes a focal point, and we're pretty confident it will, in the maturation of the next phase for both of those technological areas, which are some of the largest impactful areas that I think will really revolutionize computing, not only the quantum sector, but what's the next step after hyperscalers run out of runway, right? So that is the reason to keep an eye on Emergence Quantum, and we're excited about the future.